let's get started with today's talk. But before we talk about what we are doing today, let's first talk about what is the other thing that all companies are doing apart from writing code using AI. The other thing all companies want to do is deploy AI to their customers, right? And this is a talk about building infrastructure to do just that. But before we start with all of this, just a quick show of hands on who all have worked on building WebSocket apps before. Maybe some of you deployed it to a production, others just might have used it in their local host. I know I have 1,000 project ideas that have never seen the light of day. Okay, I expected more people, but yeah, let's get started. A little bit about me. Hey, I'm Prakhar, as the host already introduced. And over the last 2 years, I've been working on building real-time systems. Now, whether that's voice to text, document collaboration, these are the sort of things that I've been working on. Now, the topic for today's talk is building WebSocket apps that actually hold up in production. Now, what does that mean? Right? So let's think about it. What does that mean? Well, that means deploying apps that actually work in production on the remotest of systems throughout India. Now, before we talk about what WebSockets are and how we actually solve this problem, let's first talk about who our users are and what are the constraints that we're building for. In Adalat AI, we build software for Indian courts. Now, whether that's a district court, a high court, we build softwares for them. And one of the primary tools that we have is a voice-to-text platform, where the flow is pretty simple. A user would come, speak on the platform, and over some time, then the text would get transcribed and shown. Right? This is very similar to Google Dictate and rest of the other tools that we have seen around. We are deployed in 10 states, and 1,000 plus users use our platform daily. And these users are judges, court staff, things like that. But numbers are not the important part. What's important is that everything that the user said ends up on a legal document. Right? Now, why that matters? As you can imagine, data loss isn't just data loss for us. It's losing the user's trust. And if we lose their trust, what would happen? They would stop using the platform. And they would go back to the old ways of typing everything by hand. And that is something that we don't want, right? Our judicial system will come to a halt. That it already is right now on. Right? Now let's see what a courtroom looks like. This is what a courtroom looks like. And now I know some of you might have initially imagined that this has the best networks. How we have in our offices, in our homes, 1 Gbps fiber. But that's not the case here. The users that we are working with have very low or flaky networks. Now what that means is that it might disconnect at any random times, and they don't even know what a good network is, or just might not be available to them. Right? And these users don't know what React is. Some are the users that we for the first time explained what a browser is. That is the users that we are working with. They don't certainly understand what WebSockets are, and it's not their job to understand that. Only thing that they care about is getting their job done. And what does getting their job done mean to them? That the platform should work seamlessly, regardless of where they are and how they are using it. Now let's see what we are building. Right? When we started 2 years ago, this was the problem statement that we started with. That given a user that is speaking into a microphone, we'll get an audio stream, right? We'll convert that audio stream to chunks and send it to our backend. The backend has some ML models that will process it and show the output to the user, right? Sounds straightforward, right? Well, what are the key things that we're looking for? We needed a bidirectional flow that could handle huge amounts of traffic. We needed something that is low latency. And these are the constraints under which we chose WebSockets, right? Because they provide all of this, right? So we chose WebSockets. And when we chose WebSockets, we asked our AI agents to build a dictation pipeline, right? And that seemed pretty straightforward, right? Whenever the user starts recording, we will open a new WebSocket connection, right? Pass in the backend URL, handle a few events, and finally, whenever an audio chunk arrives from the user, we'll send that to a backend. And finally, when the user stops recording, we'll close the WebSocket. Now let's look at some of the events, right? On open fires when the WebSocket connection is actually established. And that's simple, right? WebSocket connection is established. Now the user can start speaking. On message arrives whenever there's a message from the server, which means in our case, it's the user's transcript. On error, maybe something went wrong, right? On close, the WebSocket closed, whether that's expectedly, unexpectedly, right? So now what would you do? Maybe the user is recording and you lost connection, right? What would someone do? They would say, okay, an on error fired, on close fired, I'll do a reconnect, right? Sounds straightforward. And that's what we did as well. But things did not go as planned. If it did, the next 10 minutes, the host could have shown you an episode of Demon Slayer, but it did not go as planned. So let's move on. What actually happened when we deployed this to production? When we deployed this to production, our users started complaining. Now, what are the things that they complained about? They complained about partial data loss. Some complained about some words getting missing in middle because we had some fancy reconnect logic. Other users complained about that they had to switch networks while recording, but one of the networks just died. These are all the realities that you have to build for. And how did you go about doing that? Well, we went back to the drawing board and we started looking at what are the guarantees that the browser provides and what are the assumptions that we made because we did not understand everything fully, right? And when we looked at that, we had some key learnings. And that's what we will talk about in the second half of this talk. Now moving on, right? We saw send, right? It is a synchronous API. And you would assume as soon as I call send, it ends up on the backend instantaneously, right? Or almost instantaneously. 10 seconds, 20 seconds. That's the max amount of delay that you would expect. But it isn't the case. So let's see what steps it actually takes, right? You call send from your code base. Then it ends up on an internal buffer. This is very similar to the call stack that we have in JavaScript, right? So everything ends up on that internal buffer. And whatever is the top is sent to the network layer, which again has a buffer. And then finally from this buffer, it ends up on the network. Now, what can happen in between, right? You called send, but the amount of time that it took from calling send to it actually ending up on the network can be huge, right? It can be 10 seconds on your device, but on a slower device, it could be 1 second, 2 seconds. And between that time, a lot of things can happen. User can lose internet, 100 other things can happen, right? So how do you know that something actually arrived on the backend? Well, we don't. Only way to know that is to build something within your application that can tell you that this message has arrived or not. Moving on. Now second thing we saw is close, right? That you close the WebSocket connection. But what happens actually when you call close? So let's say I call close, right? First thing that will happen is you will send a close message to the server. And the server will respond back with a close success message. Right? Sounds straightforward. Now, it will also terminate the TCP layer. So you have a similar process. You will send a TCP finish request, and it will respond back. Right? And then finally on close fires. Right? By the way, this close message also flows through the same send pattern that we saw previously, where it will go to an internal buffer, then network buffer, and everything is the same. Now let's see what happens if the user loses internet. So the user lost internet. We sent a close to him to the server. It did not reply back. Well, how could it? We are waiting, and till what point will we keep waiting? We'll keep waiting for 60 seconds to pass. That is the timeout that Chrome has built. And once that timeout passes, that's when onClose will fire, right? Now you might think that 60 seconds is not a long amount of time. So let's count down till 5, right? 5, 4, 3, 2, 1. Well, that is just 5 seconds. So imagine if someone had to wait for 60 seconds, how long that would be, right? Now another problem we have is, how do we know whether a WebSocket is disconnected from the internet while we are recording, right? So that's where a classic solution that a lot of other people have built as well, this is not something new, is to build a ping pong solution where you would send a keep alive to the server, and the server will respond back with keep alive acknowledged, right? And this process keeps on going. But what happens when network drops? When network drops, keep alive will not receive by the server, right? And the server will not respond back. And another time, if we send it, the server does not respond back. Well, when this happens n times, we can assume that the connection has dropped, and we can force a reconnect, right? That solves half our problem, that whenever we know that WebSockets are disconnected, we can reconnect. But again, that's just half of the story. Because these WebSockets is not the only thing that we are using in our code base. There are a lot of browser APIs as well. So let's look at some of them. Right? The first API that we are looking at is navigator.online. Now, if you look at it, you would think, okay, this API will tell me that a user is connected to the internet or not. But that's not the case. What it tells you is that the user is connected to a network. And connected to a network and connected to internet are two very different things, right? Now, there are some other things as well. Knowing that someone is connected to a network can be useful. And if a network has changed, might be useful, right? Maybe they switch networks, you want to log that. So it is a useful information. But even though it has a corresponding on-change event, suppose if you go from a Wi-Fi to hotspot, it will not register that because it went from a true value to another true value, even though for a few milliseconds you were not connected to any network. So these are the sort of flaws that it has. Now let's look at some other APIs. Set timeout, right? This is an API that we use daily. I think almost all of us has used it at some point. Now what does this API take? It takes a callback and a timer, right? Now when the timer expires, what is supposed to happen? The callback is supposed to execute, but it does not execute immediately. It has to wait for the call stack, right? Now waiting for the call stack can be a small amount on your machine, but think about background tabs. If the tab is paused, all of these things can mean that set timeouts could fire much later than what you anticipated, right? And if you had this in your keep alive logic, it would fail, right? Let's look at a set interval. Now, we use a set interval, and we would again assume the same thing, right? Okay, it's expected to fire on time, but what you would see is that over time it loses cycles. So, the first time it fired on time, next time it lost 20 milliseconds, next time it lost 48 milliseconds, and this keeps on going. Until, well, think about this, so you have done the same process thousands of times, and your delay would not be, hey, 20 milliseconds, 100 milliseconds. It will be over multiple cycles, right? So you end up with a delay of 100 seconds, right? Now think about this, so you started a timer of 1 second, but the timer is firing on 100 seconds before, right? Every logic that you wrote will broke. So you need to account for this time whenever you use intervals. Now let's come back to the start, right? We call new WebSocket APIs, right? Sounds straightforward, right? This will make a connection. Now let's assume the backend is not available due to any number of reasons, right? What would you assume? Either this API should give you some error, or there should be an on error, right? Something should happen, right? Well, in some cases, it does not. It has no timeouts, so you are stuck waiting, and the user never knows, okay, connection has timed out, we need to reconnect, something has happened, right? So that's why whenever you use this API, you need to ensure that you build manual timeouts. Moving on. What does all of this mean in practice? Right? All of this is towards one goal, that whenever a user loses internet while recording, we don't lose data. His experience should be seamless, right? And we want to resume our WebSockets from where we left when we were online and not make the user restart their session. That is the key goal that we are building for. Now, how do we go about doing this? Well, the first thing is we need to keep track of how many messages were sent and received on each side. So the client keeps track of, okay, I sent 20 messages and I received 35 messages. The server keeps track of, I sent 15 messages and I received 20 messages, right? And both the sides know this, right? If they get the other side's number, they can know what is the gap. But the knowing the gap is meaningless if you cannot fill that gap. So that's why we need buffers on both the sides. So let's first look at the retransmit buffer, right? We saw in the keep alive logic, right, that is the maximum amount of time and we will have when we not know whether this connection is connected or not, right? In our seconds, if we cap it at 2 keep alives missed, that means 3 seconds, right? So what we can do is we can build a scrolling window that keeps every message that was sent for the last 3 seconds in this retransmit buffers, right? Now let's look at message queue, right? Even though we know that the user is offline, we don't want them to stop recording. They should still be able to continue, right? The network might come back at some point, right? So that's why we have a message queue. Anything that comes after we know that the user is offline ends up on the message queue. On the server side, we have just one buffer. Whenever server sends something, it'll always put it in the replay buffer. Again, this also has some limits. We'll only give last 1 hour of messages, but that should be fine, right? No one expects the user to be offline indefinitely. Right now, how do we go about sending where each clients are, right? So first thing when you do is when the client opens a WebSocket connection, what it will send is a sequence number. Now, what does this sequence number tells us? It tells us the last message that the client received. Now, another thing that we send to the server is, another thing that we send to the server, from the server to the client is number of messages that the server received, right? Now, both the sides know how many messages the other side received, right? And this is the clear gap, right? Now, another thing that's important to note is, what is the server ID? Why is that important, right? Suppose if you are keeping these buffers in memory, right, and something happened, one of your pods died, right? could happen. It's a Kubernetes cluster. We need to keep in mind that that can happen and inform the user that we have potentially lost their data. Let's be honest about it when we cannot do anything, right? So that's why we have the server ID. The client compares the server ID. And this is a different server ID from what we started with. We just tell the user, okay, we have lost your data. Sorry. Right? Better be honest than tell false information. Right? So what does this mean in practice? What it means in practice is that whenever we lose data, we just tell the user, okay, hey, this is a server sequence, this is a sequence that is on my side, compare and retransmit everything that is missing, right? Sounds straightforward, right? You retransmit whatever is the delta. Well, that's what we did, right? And that's most of my talk, but it's also important to see how this works like in real life, right? So now let's look at the screen, right? What you can see is a client and a server, right? And all of the things that we talked about, having a keep alive, is their heartbeat working, right? Now, let's see this in demo. What I'll do is how any connection starts, right? We'll first connect the WebSocket, right? The ready message arrived, as we talked about, with the server ID. Now we'll start recording, right? Recording has started, and you can see that had some connection packets have started flowing, and this is what we expect, right? That some packets will flow from the server to the client, client to the server, and everything is fine and dandy. But what happens if we disconnect? Well, if we disconnect, right, we don't know. The client does not know that it's disconnected. It needs to wait for the keep alive, right? After two keep alives are missed, that's when we actually know that we are done, right? Now, when that happens, we wait for the user to connect. And when the connection happens, you will see that server tells you, okay, I received 3 messages, and now the client can retransmit, the server can retransmit, and all of these things can happen seamlessly without the user knowing, in most cases, that they were even disconnected in the first place. So yeah, guys, that's been my time. I'll just show you a quick URL. Now, you don't want to discover this the hard way. So there is some links on this QR code. It's a blog about some of these learnings, a link to our careers page, and a few more things. So check this out. Thank you.